Recording this now. There we go. Okay, so you're not going to have to dig into the guts, and I'm not going to talk about this technical specifications if you want to sort of sit down and create one out of sort of standard tools on your computer, largely because you should never have to do that. We have a number of tools, which I'll show you about how to create a new one, how to make edits, and then how to work with them in R and Python and MATLAB. To avoid the details, but having at least a conceptual understanding of what's inside can really help if as you're trying to either develop some custom workflows or, oh, that's funny. Yeah, thanks, Estelle. I'm recording it now. I actually just saw your message and I'm glad that I remembered to record it anyway. Okay. Okay, so here we go. So a lipid is essentially just a big container that can hold lots of things. And so, this is the logo, but then we zoom out and we see that sort of the whole black circle here would represent everything that's inside there. And so we'll just take a tour through this, and it's a very nested in hierarchical format, which is why this sort of Prezi works well to be able to zoom in and zoom out. So, okay, so at the very beginning, there's just going to be some metadata about this data set. There's a lot more than this that typically gets included, but at the very least, there's a data set name, which typically follows this structure. It says it's about the site name, the last name of the first author of the publication, and the year it was published. It has some sort of URL from where the data originally came from. There may be some information about who are people involved, and again, a whole bunch of other things that describe the data set as a whole. Each lipid data set, the granularity is a little bit fuzzy. It tends to be something somewhere in the intersection of a site, which can be sort of loosely defined, but a single geographic area, which is typically smaller than 10 kilometers, but is typically much smaller than that. So like a lake or a stand of trees from which a bunch of trees record, or a cave. So there could be multiple sites within the lake or within the cave, but that would all be included in the same data set typically. And there's sometimes an intersection of that with publication. So we'll talk more about that here in a second. Okay, and then there's, in addition to those sort of root metadata, there's these 5 major classes of information, 3 more types of metadata. One about the geographic information, so where did this thing exist in the world? Another one which describes the publications, which describe the data. And then another one which describes the information about what funded it, who funded it. And then the actual data themselves and more metadata describing those things which are split into the Paleo data and the cron data. So typically Paleo data, this is anything that would be describing the thing in the past that you're interested in understanding. So this could be Paleo climate, Paleo environmental, paleogeographic, all kinds of different information, but this is distinct from the cron data, which is the data that you measure to help you understand when those events in the paleoclimate and the paleo data happen in time. So we separate, and as long as you're not, well, so typically you can think of the paleo data as the y-axis data and the cron data as the x-axis data in your standard plots, so long as you're not doing a downcore plot where you turn the axes. Okay. So let's think a bit more about the geographic metadata. So again, here's a simple example. We would have at the very least a latitude, longitude, often something about elevation, some name of the site, a country, a state, other political or geopolitical information. Often, again, much more. In the publications, it's just what you imagine. There's one or more publications. For the most part, these data it's certainly appropriate to work with lipid files with data that you're developing that aren't yet published, in which case this would be empty, and that's okay. But then once it gets published and archived online, we'd want to include this to help make it easier for people who use it to cite that information. And then funding metadata, which is, I would say, probably the least commonly used, but there is spots here that if you want to keep track of who paid for it, funding agencies really like to see that. Okay. Now into the interesting parts. So we're actually going to start with the cron data here because the structures may be a bit more familiar. Again, one of the major design principles for lipid was flexibility. And so essentially anything that you see one of, there can be multiple of when the situation require. So in the cron data section, you can have as many cron data objects as you need. Again, this is flexible, but generally speaking, this is designed to correspond to sort of physical samples. So you can imagine you go to a lake and you take 2 cores, and then ultimately you composite them together into a third core. That could be these 3 objects. So cron data 1 would be all the things you measured and worked with on that first core, and cron data 2 would be all things you measured on the second core, and then there's some sort of theoretical physical object that is the composite of those 2 that might look like this. Or this could just be 3 separate physical materials. And this would more or less correspond to the same thing in paleo data. The structures of the cron data and the paleo data, they mirror each other, so that whatever they each have measurement tables, they each have models, they each have summary tables, and they each have these objects which more or less correspond to physical samples. So if we zoom into one of these, within one of these, there's different types of these sub-objects. Ones which are measurement tables. This is you can just think of this as like the spreadsheet of stuff that you measured on that physical sample. And they can have models. And this would be some sort of statistical output, typically of something that you're modeling based on those measurements. And so this is hopefully familiar to most of you, because we use this in like age modeling, right? So the measurement table would be all the lead-210 or the radiocarbon or the OSL data that you actually measured on that sample. And then the model would include all of the information from the age depth model, which used the measurement table, but then also some inference, and then produce new data that we want to keep track of. So we can take a look at this in a bit more detail. So this is really straightforward within a measurement table. There are a bunch of columns, and a simple example would mean there's something like depth and radiocarbon age and some uncertainty in those radiocarbon age, and maybe some text data too that talks about describes it. Could be notes. It could be something like this. It says, what was it that you dated? And it's not uncommon for there to be dozens of these columns. There can also be multiple measurement tables. So say you measure, this is more common in the paleo data, where you might measure, say, one proxy at centimeter resolution, and then you measure a different proxy every 5 centimeters. And it's possible to put them all in one table, but it's awkward. And so we can have multiple tables too if we need them. Okay. If we look at the model, inside the model is, again, just more tables and some more metadata. So first, there'd be information on the method. And so as you're working through the age modeling tools in GeoChronar, all of this will be happening behind the scenes. That if you run Bacon to produce an age ensemble and age model, GeoChronar will keep track of the parameters that you use and will write those into the method. So if you save your lipid file in the future and you're wondering, oh yeah, what parameters did I use for that model? It's there in the metadata. Right. So it could be something like just the parameters and the run environment, or even the line of code or the series that you use to generate that. And then there's these 3 different types of tables which are stored within models. So the summary table is the one that you're probably all most familiar with as you're thinking about output of an age modeling algorithm. And it looks something like this. It's going to have some sort of depth, typically on a regular scale, like every centimeter, something you asked for. Oh, that's not, okay. And then it's also going to have these outputs. So something like the median age, and then some sort of uncertainty around those median ages, right? It summarizes the statistical output, but doesn't give you the full distributions. Okay. Okay, the actual full distributions are what we really need for GeoChronar. After this, Julian's going to talk a bit about the theory and the logic behind using ensembles for uncertainty quantification. But the idea here is that essentially all modern age modeling algorithms use some type of ensemble-based approach, meaning that to quantify the uncertainty, they run many hundreds to sometimes many thousands of plausible alternate scenarios that are comparably, if not identically, consistent with your both assumptions going in and with the measurements that you made. And so, for example, if we take bacon, for example, bacon will generate, I think, several million of these, and then we can export just a subset of those, and then we can look across them and see what these plausible alternate histories were, and then propagate those through our future analyses. That's the big idea behind geochronology in general. So what these ensemble tables looks like is there's one table of depth, which is like the same depth as the output on the summary table. But then there is going to be typically about 1,000 of these age ensemble members, and they're and these are all just different plausible realizations that we can then store here, and then propagate through our analyses and subsequent analysis. Okay, and then the third one is more for when this is primarily for radiocarbon data. When it gets calibrated, you get these weird empirical distributions, and we keep track of those distributions here so we can plot them. Is the main reason for them, but they get stored here. So this is also relevant, I suppose, if calibrations change and other similar things. Okay. So this is just age and the relative probability of that age. Okay, so that's what's in the cron model. There can be multiple cron models. So in fact, you're going to do this. You're going to create one model using bacon and another model using bcron. And we're going to store all that information, each in their own block, and we can reference them or use them in subsequent analysis. Okay, so this all it can be quite a lot, although this is the vast majority of data sets don't have this level of complexity in terms of multiple models, but they can. Okay, so Paleo data has the identical structure, but it just sometimes has more additional metadata down at the variable level that we'll highlight here. So just like this, Paleo data, there's multiple Paleo data objects that typically correspond to physical objects. Within each object are measurement tables. There can be models. They are less common, but the example of a model would be, say you have some sort of reconstruction algorithm, especially one that's ensemble based. Maybe it's some sort of Bayesian reconstruction algorithm. We can store the output of those ensembles, and then we can also have ensembles in your Paleo axis as well as your cron axis. Again, those are relatively uncommon, but the capacity exists if you are interested. Okay, so in our Paleo measurement table, we would typically have all the things that you measured on say the core or the material that you measured. But then also it would have sometimes things that aren't measured, but that are inferred from a model or estimated. And they're here primarily for convenience, and that we also often want to make this comparison. And there is a distinction in terms of the metadata between inferred variables and measured variables. I think this will zoom us in. So depth, that's something we measured, but then we have here like this would be the median output of your age model that correspond to the depths that you measured, right? And so we have the age there. And then we have say the delta 18O that you measured, and some metadata about that, including like the units and the values and whether it's measured or inferred. But then we can also have these additional types of metadata, which are really helpful if you're working through large compilations. You want to be able to screen or filter the data based on, say, how did the authors interpret this? And so, it's common for Paleo data variables that have interpretations, which describe the climate interpretation or the isotope interpretation, and could say something about, what is this interpreted as in some sort of standard language? What's the seasonality? What's the relationship between the original variable and that interpreted variable? And how do they know? This is often like a quote from the paper. So some great things there. It's also possible to actually embed a whole proxy system model at the variable level here, although again, not super common. And then you can also have, so that would be the actual measured variable that to know, but in this case, maybe it's been calibrated to precipitation through some sort of inversion model. Again, we could have interpretation on this one too, which is more or less just the same thing as the variable since it's been calibrated. And then also details on what that calibration looked like. Okay, and then things like uncertainty and notes and lots of other stuff that we saw in the other table too. Okay, so that's the whirlwind tour through the structure of yeah, so there's also models, I guess I mentioned this already, that would have a similar structure to the age models, but would be built around something that's focused on the paleo space, which is not something we're going to be talking about in this workshop. But you could use it. And GeoChronar, if there are ensembles in both the cron data and the paleo data, will then integrate those two uncertainties when you're propagating things through. Okay, so I'm going to show you a bit more lipid things on the more maybe practical side of how you create and find lipid data, and you'll get some more practice doing that during the hackathon. But are there any questions about the structure at this point? I'll also ask later if that's easier. Okay, it seems like you're all with me, or at least we'll know how to find the recording if you want to go back and try to follow that up again. So, so I'm gonna spend the next 10 minutes or so with the whirlwind tour here of some of the tools that let you create and find lipid data on the web. Okay, share screen. Okay, this is the whimsically named Lipid Playground. The website is just lipid.net. So lipid.net is a website that we made. It has just some information about lipid, and if you want to know some of the technical details, and there's a whole bunch of stuff in here. But the most powerful part of this website is the playground. And so this is an interactive website that lets you create or edit lipid files. So if you have some data that you've collected and you want to make a lipid data set that you can then use in GeoChronar, this is by far the easiest way to do it, especially if you're new to this. It is possible to just do this in R, but it's tricky. So I would strongly encourage you to use this. If you're new, I'm just going to go a quick tour, but you should, there's this take the tour button, which is great because you can see all these dots. There's a lot of steps. There's a lot of, and this will walk you through all the things that are happening there. Okay. So this is going to look really familiar, right? So this is the root section where you can enter the dataset name and who created it and what type of archive it is and some notes about it. You can you could add some metadata about your funding sources. You could add publication metadata, and one of the coolest things, this is one of the coolest things about this website, is that if you have the DOI, I should have an example somewhere. I don't have one easy to hand, but if you have a DOI, you can just paste it in here and push autocomplete, and this will get the information from the DOI server and auto fill in all the rest of the publication metadata. And then you can go through and enter your geographic information, all the metadata, and then come down here and create paleo data objects and paleo data measurement tables that you would use so we could, imagine you're starting from scratch and we're just going to go to column 0. This is Python based, so it uses 0 base indexing. And say that it's lake sediment, and it's the variable here is depth, and the name is depth, and the units are centimeters, and then we could add another one. Nope. Add a column, and then come in and do more work here in terms of, measured, and this is D18O per mil. And then you work through this, and it takes a while, and then you can add interpretation metadata and then copy and paste your data into a little spreadsheet down here. Again, creating one from scratch will take a bit, especially when you're learning the platform. But you can also upload files from your computer. My computer is not happy with me. So here's actually one of the ones that we'll be working with for the workshop. I'll upload to the server, and then all this information will be already filled in because this is a file that already exists. You can see where this thing is in the world. You can come in here. You can take a look at so you can see how that works. Ha, that's funny. It gave me an error right now. And then, here's the geographic metadata. We look at some of the measurement tables as they exist. And so all of these things have metadata in here. Here's a calibrated temperature variable, which has and then some interpretation metadata all built into this. And so if you needed to either correct a mistake or add some information to this file, you could upload it here. A really important tool to know about is that after you finish working it, there's this workflow button which says validate. Push validate, that's really good. And hopefully you get this green button that says a valid lipid. If you don't, it will tell you what's wrong. So in this case, there's a warning that's missing funding, but you don't have to have funding information. So it's fine. And then you can download this to your computer. There's also this button here, which lets you, if you want to submit your record to the World Data Service for paleoclimatology, we've worked with them there's some additional metadata that they want. So they'll ask you to switch this on, push OK, and then there'll be some additional fields they'll ask you to fill in. And when you're done, you click this button and it will export. It'll export this to a text file that you can then work with Bruce and Wendy and the folks at World Data Service Paleoclimatology. I wonder, this is interesting. So hopefully we're not going to have web servers with this today, or maybe we're just hitting it too hard with a lot of people right now. But if there's something down, then we'll fix that. Anyway, what that would normally do is you just download a text file, which is in their formatted archival format. If you are, so this is, and then also if you want to just make a quick graph to make sure that things look the way that they should, you can do that here. It's not, it's quick, but you quickly see to make sure that, my data look right, or my data don't look right, or even explore it a little bit here.
Hey, Nick.
Yes.
There's a couple of interesting questions in the chat. Do you want to take those?
Yeah, okay. I see. Okay, so how much of the data from Neotoma is converted or available, and is that accessible from the lipid site? Yeah, great question. So, so we have collaborated with the folks from Neotoma a lot and we've had various iterations of a converter. So Neotoma does an excellent job at archiving and curating assemblage data. And that's something we don't want to try to replicate. And so, so rather than hosting lipid versions of Neotoma data, we would much rather just be able to convert them to lipid data on the fly and then work with them in these analysis tools. And so, yeah, so you may or may not know that, so there's a Neotoma package in R, but Simon Goring and Socorro Dominguez have been working to update that to their new API, and they're almost done. So either in the exact home for it is in the whether it's going to be in the LiPidR package or in the Neotoma 2 package, but there is a Neotoma to lipid function that currently exists. I can paste I'll send you a link afterwards. It's just they're not quite done with their side of it yet, so I haven't been able to finish my side of it yet. So it actually will do everything. It'll convert everything from if you give it a Neotoma link, except for the Paleo data part of it. So all the assemblage data, but all the metadata and the chronological data currently work, and I can send you a link of how that works. And within the next month or two, that should be fully functional. And so when that happens, I'll also add some examples of how you would take a Neotoma data set and then start a workflow into GeoChronR. But the short answer is it's one line of code. You say Neotoma to lipid, and now you have a lipid object in R that you can then use in GeoChronR. Cool. Okay. So we'll go a little bit over time, and that's okay. the last place I want to show you is, wow, why is my computer so angry? Is the lipidverse. And so this is not a long-term data repository, but it is just a spot where we provide easy access to a lot of the compilations that have come along, and over in the not too distant future, it's going to be getting an overhaul and include some querying and some nicer graphics and some other functionality that will make it even more powerful. But for now, this is a great place to find lipid data that you can start with that are generally well curated, although often not perfect. And so, for example, so here's some of the major compilations which exist. In the first exercise today, you'll be exploring the temperature 12K compilation. And so this is, again, it's not super sophisticated, but you can find lipid data here, get quick visualizations of, so this is a pollen and for temperature reconstruction here, just see a bit of what it looks like, but then you can download the lipid file here or get the link to it, which then you can plug directly into R. Or if you see a mistake or want to make some, or add something to it, if you click edit, it will take you straight back to Lipid Playground